In this video, we will look at the underlying concepts behind correlation. Oftentimes in statistics, we are called to look at two quantitative variables. There are many ways we can look at quantitative data, depending on what our goal is. You can look at each variable individually, histogram and descriptive statistics, which we've already done. Also, the two variables can be graphed and their relationship using a scatter plot. A numeric summary called a correlation coefficient, R, may be calculated. A linear regression equation, a prediction line, can be found. Multiple regression with multiple predictive variables is possible, but not covered in this class. And finally, two quantitative variables can be analyzed with a hypothesis test to see if there is a statistical significant relationship present. Correlation has to do with the patterns and relationships between two variables, the explanatory variable, known as the independent variable, and the response variable, the dependent variable. Correlation specifically looks at the relationship between two quantitative variables and focuses on looking for a pattern between them. The graph of the data for a correlation is a scatter plot, and each plot or dot represents two pieces of information, a value for the explanatory variable and a value for the response variable. Let us say we're interested in the relationship between manatee deaths in Florida from powerboat collisions and the number of powerboat registrations. This data is on the same content page as the video. What would the explanatory variables and response variables be? The explanatory variable, the independent variable, would be the number of powerboat registrations in thousands. The response variable would be the number of manatee deaths. We can graph the variables as histograms, and we graph the correlation between these two variables as a scatter plot. When we look at the scatter plot, we describe it by four different attributes. The overall pattern, is it linear, curved, or no pattern? We identify if there are any deviations from that pattern, like outliers or data gaps. If the pattern is linear, we need to indicate if it's positive or negative. Lastly, we describe the strength of the relationship. By strength, we mean if the dot pattern is very obvious and the points are close together, which would indicate that it's a strong relationship, or dot pattern is not very obvious and or the points are far apart, which would indicate it's a weak relationship. Strength of the relationship is a continuum. The manatee death in relation to powerboat registrations would be linear. There are no clear deviations from the pattern. It is positive and strong. The correlation coefficient, known as R, describes the strength and direction of the linear relationship. Positive or negative describes the direction, and the absolute value describes the strength. The weaker the relationship, the closer that absolute value is to zero. These three graphs show you the R value and scatter plot. You can get a sense of direction, positive or negative, and strength, strong to weak, from these graphics. There are a few key facts that you should remember about the correlation coefficient. Outliers will have a strong effect on the value. If there are restriction or big gaps, those will also lower the strength of R. We assume that the variables are each normally distributed. Most importantly, correlation is not causation. Just because two variables have a strong relationship, it does not mean that one causes the other. There could be a confounding variable. The confounding variable is actually affecting how those two variables interact. The R value is important on its own because it tells you the strength and direction of a relationship. It is also important because when you square it, it will become the effect size, the coefficient of determination to be precise. As you will recall from the two sample dependent and independent t-tests, an effect size describes the variability of the variables. The interpretation of this R squared is the same as R squared that you have previously calculated, which is the percentage of variation in the response variable, the dependent variable, which can be explained by the explanatory variable, the independent variable. As an example, 25% of the variation among children's IQ scores is associated with the variation in their parents' IQ scores.